Good evening, everyone. Welcome to today's special lecture organized by Nepali Society of Student Researchers, NSSR. On behalf of NSSR, I warmly welcome all student, researchers, faculty members, and guests joining us today. We're delighted to see participants joining us from different institutions and locations. NSSR is committed to creating opportunities that connect aspiring researchers with experienced scientists and researchers all around the world. Through lectures, mentorship initiatives, and collaborative programs, we aim to foster a strong research culture among students and young scholars. This session offers a valuable opportunity to learn about frontier of experimental physics, large-scale scientific facilities, and the pathways that connect student to international research environments. I would like to request everyone to keep their microphone muted throughout this session to ensure a smooth and distraction-free experience. If you have any question during the presentation, please feel free to type them in the chat box. We will reserve the time for discussion during the Q&A session following the talk. So moving on, our guest speaker today stands at very leading edge of modern experimental physics. His academic and professional journey is an inspiring blueprint for many of us in the room. It is my great pleasure to introduce today's distinguished speaker, Dr. PASHUPATI DHAKAL. Dr. DHAKAL completed his master's degree in physics from Tribhuvan University, Nepal, before pursuing his doctoral studies at Boston College in Massachusetts, USA, where he earned his PhD in physics. He currently serves as senior scientist at the SRF Institute within the Thomas Jefferson National Accelerator Facility, widely known as Jefferson Lab, one of the world's leading research centers in accelerator science and nuclear physics. Over the past decades, his pioneering work has advanced superconducting radio frequency technology, the very engineering that powers modern particle accelerators. Alongside his lab research, he serves as Associate Professor of Physics at Old Dominion University, mentoring the next generation of physicists. He has also been a pillar of leadership for the broader diaspora, serving as the president of Association of Nepali Physicists in America, ANPA, from 2024 to 26. With dozens of peer-reviewed publications and deeply rooted passion for student mentorship, he joins us today to deliver a talk titled Frontier Experimental Physics: How Large Research Facilities Advances Science and Global Opportunities. Ladies and gentlemen, please join me in welcoming Dr. PASHUPATI DHAKAL, sir. Sir, the floor is yours.
Okay, thank you, Diksha. I think probably I'm the new here. Probably I don't know your initiative, but looks like you guys have done great work to give the at least a platform to have a discussion about the physics and in general in the context of Nepal, and then reaching out to the people outside the US, which is outside the Nepalese, which is also very good. Before I start my talk, I think I personally like to thank one is Manish. It's Manish. I think he reached out to me, and then I say, okay, I can prepare something. And so the topic is Frontier in Experimental Physics: How Large Research Facility Advance Science and Create the Global Opportunities. I made a couple of the slides, so let me try to share here. Can you see my slide?
Yes, sir.
Okay, does it look good?
Yes, it does.
Okay, good. Okay, once again, thank you for the nice introductions. It's my pleasure to be here. And then I'm gonna go through some of the slide. I like to make it interactive because I'm not 100% sure the goal of this organization, but I'll try to answer as much as I can. So you can stop me anytime. If you have any question, raise your hand. I have a split screen so I can see it. And also if you have any question, you can in the chat box, you can also type it there. So okay, let's start it. just to give you an about outline, who am I, just to give out myself. Jefferson Lab, and then it's also one of the national lab in US. How does it actually operate in US? And then how is that very important in terms of Nepal too? Can you do something like that? And I'll briefly go with my research area just a little bit, because I don't want to make like a full my research talk in these presentations, but if you guys have any more questions, and then I'll be happy to answer it. Academic and professional journeys. It's been a long time. Born in one of the village back in Nepal. I also put my birthday. I'm quite old for now. 1977. I did my SLC as typical. I finished my ISC and BSc from PN Campus Pokhara. Moved to Kathmandu for my master degree. I would say my master degree was also one of the turning point in my career. Before ISC and BSc, I did not really know what should I do for the research. But after I coming to Kathmandu for my master degrees, I started learning a little bit more about physics, and then also the opportunity that if you do good, you can you will have more opportunity to afterwards. That made me to look for outside. I briefly taught at the Central Department of Physics and also the Himalayan White House College for about a year at the gap year. And then moved to USA in 2004, did my PhD in physics from Boston College in the condensed matter physics. After that, I moved to it's called Jefferson Lab in short, which is also Thomas Jefferson National Accelerator Facility, located in Virginia. I started as a postdoc. I thought I'm going to stay here for 1 year, and then turn out that I'm here for another this is my 16th year working as a staff scientist. Started with the postdoc, and now I'm the senior scientist at the Thomas Jefferson National Accelerator Facility, also called the Jefferson Lab. Also, meantime, I am also appointed as a associate professor in physics in the Old Dominion University, which is very close by, so that I can have access to the mentor the students, and then the student can come to Jefferson Lab and do their scientific research. So it's quite long. Just to give you an example, just a short brief of what is Jefferson Lab is. Jefferson Lab is so the United States started this having a concept of the national lab system right after during the World War, where they need to develop the technology super fast, and because there's not much of industry that can actually take the lead. And then if you know, most of the industry, they like to make a profit, right? So the government, if the government needs something, they need to do by themselves. So they started having this national lab system, talking about the oldest one, the Oak Ridge National Lab or the Los Alamos National Lab, basically famous for the making an atom bomb. And later on, they expanded this national lab system. Right now, they have the 17 national lab around the US, and then Thomas Jefferson Lab is one of them. Other labs are much bigger than Jefferson Lab, but some of them are very smaller too. But Jefferson Lab is very famous about one of the technology is the accelerator science and technology. I'll talk briefly later on. And then also that accelerator is used for the nuclear physics research. And this is one of the kind in the US at that time, but these days there's a couple more being constructed. On the middle figure, you can actually see the aerial view of the accelerator system. Everything is underground, about at 10 meter deep from the ground level. All the accelerator and research lab is also underground. So if you see, let me turn my pointer. If you see the circulars here, these are the experimental halls, basically the labs, which is as big as a movie theater. So then all the instruments are inside there. Just to give you the layout of this, what it actually looks like underground. Basically, the Jefferson Lab is used a very powerful electron source. So we call injector from the injector. And the accelerator around this, we call the racetrack, is about 1 kilometer in distance. The electron gain an energy using these superconducting cavities, and then it goes around, and when they go around and around, they gain more and more energy. And then depending on your experimental need, you can take these electrons to the very different experimental hall and do your experimental research. So this is basically Jefferson Lab is so far, it's just a fundamental understand how everything is made up beyond the standard model. So what is famous about this the Jefferson Lab is about 2,000 scientists from more than 275 institutes, university, and also the research lab from 35 countries come to Jefferson Lab to do their research. So basically our lab is, when it's running, it's run 24/7. About 1/3 of the US nuclear physics PhD in USA are actually based on the research carried out at the Jefferson Lab. So whatever there is a PhD in nuclear physics from, at least from USA, 1/3 are actually the research done at the Jefferson Lab. Right now, about 200 students are doing their PhD research based on the experiment that are being at the Jefferson Lab. We not only do the experiment, we also have some theoretical people. They try to work as a theory and then try to validate their experimental data. Just to let you know some of the what our Nepalese communities, the Nepalese students are benefited. I couldn't get the official data so far, but I still believe that there are more than 20 Nepalese students that actually did a PhD based on the experiment at Jefferson Lab. And right now, even right now, there are about 10 students working actively on their PhD research. And Jefferson Lab, right now, we have 6 scientists working as a staff, which are of the Nepali origin, including myself. So what this Jefferson Lab is, basically we use the electron beams. There are several accelerators around the world, but this is one of the kind where the electrons is relativistic electrons, basically struck into the fixed target. Also, you need to also understand the collision and the nuclear physics research. So you have a fixed target. The electron beam actually can break the protons and neutrons, or even the not only the nucleus. And I'll try to understand the quarks, how they are a stronger force and how they are binded each other, and also the phenomena like how what is the binding force between the quarks, basically gluons, and also understand the nucleon spins and investigate the nuclear momentum. The CP violation experiment, and several other things, including basically around the nucleus, so protons and neutrons. These are the experimental halls. You can say, I said earlier that we have 4 experimental halls, means 4 experiments are running at times. Some experiments can run for almost more than a year or 2. Some are short experiments, runs for 1 week or 2 weeks, and we have all this data or the collision, all the data is saved, and basically the students, they can make their own target, they do the collision experiments, save data, analyze, publish, those kind of things. So when the experiment is running, we're running all the time. These are the examples of one of the halls. You can even imagine one of the scientists is staying right here, and this one is basically the detector. So when the collision happens, with the high energy electrons bombarded onto the atoms, so we just look for all the fragmentation coming out. Depending on the momentum and the energy, then you can identify which particle is coming out from this, the collision experiment. So the federal agencies, there are many federal agencies that actually fund this research program. I listed as some of the summary here. And every federal agencies, the government agency has some particular interest on this one. So they fund the fundamental research as well as some applied research. For example, as I said earlier, our lab is under the Department of Energy Science, which has 17 national labs. This basically supports the high energy physics, fusion reaction, material science, superconductivity, quantum science, and accelerator. And basically, this is the largest supporter of the physical science research in the United States. There is other agencies, for example, the National Science Foundation, which basically does all the physical science research and also some social science research. And this is primarily used for the non-medical, means you can also do some medical physics research, but mostly support the higher education, means universities, professors, students, and they get the grant from the National Science Foundation, and they can conduct their research. And also, depending on what kind of application, NASA has their own, because it works for the space. If you need to further the defense, Air Force has their own research laboratory. Army has their own research laboratory, and Navy has their own research laboratory. Agriculture has their own research supporting system. The medical physics, you can also say the National Institute of Health, which basically support a lot of medical physics research, and also the Center for Disease and Control Prevention, which is CDC. And also the funding mechanism is in such a way that they characterize not everything is under one umbrella, but they also divide into the different research group, and then all the funding comes from that way. The contribution to the national lab is also which is also the Department of Energy. So far, there are 129 Nobel laureates who are affiliated within the Department of Energy National Lab, and then also the other labs. This is one of the broad perspective of this one. So basically, the national labs, they don't actually develop the product. They host the big user facility that is impossible to maintain by the private company or any universities. For example, the large synchrotron light source, large superconducting facilities, and also the particle physics that can be used for the material science or the nuclear physics, and nuclear reactor, for example. So it's the closed cycle. So you can go to this national scientific user facility, do your research, and then at some point, if something good happens, also not only the universities, but also the company can come and do their research. So if they gain something, and then finally it can go to the commercialization means. So the main idea behind this, the government funded the research is not only not for the actual product, but also to support the company so that they can have this the partnership with the private company, and then make things that useful to the general publics. So this is one of the screenshots about this, how the research works. Like that's totally different. And other company, the other countries versus the USA. So if you look at the basic research science, the fundamental research science, the government plays big role, about 40% of this the funding provided by the governments. There are some other business also does some research. The large big company, Apple, Google, or Intel, or the Microsoft, IBM, those also the bigger company. They invest a lot of time and money to do this research. But in also the higher education, the bigger universities, or even the smaller university, all of this contribute to the basic research. But when it comes to the applied research, now is the federal government starts to fund less, where the business starts to pick it up. Means when there is something they think is applied, then the technology or the research they did in the national lab or the federal level, they slightly give that technology to the business. And doing to the business means business pick it up, and then the federal government keep doing this basic research. But if you have to go to the development side, so if you need to make something, then the federal government, okay, we are out of the hand, but still support this business, and it's called a public-private partnership, where the business pick up a big chunk. This means now you have a commercialized, so everybody can benefit of this one. Sometime the one of the good thing about the US is, if you think there is something we call the valley of death, means there is something, it has a high risk and high reward kind of things. As I say earlier, in the beginning, where there is a basic technological research, the public funding, means that's we call the government starts to invest heavily. Private companies do not even care about it, because private knows that if they can't make money, they're not gonna work on this one. And so in that case, the US government fully support those ideas. For example, all of this national lab system. And when there is also we know that there is something can be made, or you can have a commercialized, then federal government transfer this technology to the private companies, and private companies make it happen. But in some cases, we call the valley of death, means there is a high risk and high reward. In this case, there is a public-private partnership, means government say, okay, I'll give you $1 million, private company, you get $1 million. And if you have this one public and private partnership, the technology have the growth very fast. Currently, one of the example right now is the COVID vaccine. And during the COVID vaccine, there was no vaccine in that time. The US government put a lot of funding, and then company also did a lot of resources, and then within a year we got a COVID vaccine. Right now, the biggest investment right now the US government doing right now is the quantum computing, because the quantum computing is one of the challenging thing, because if the company starts to taking over, they have no idea whether it's going to work or not. In this case, there is a lot of funding coming from the government side, where the private company actually picking up that parts, and hopefully in another 5-10 years we'll see something useful out of the quantum computing. One of the idea in the why US is always the forefront of this technology is they continuously innovate. So if you cannot continuously innovate, it's just prepared to shut down, just find something else. And in the beginning, the government also supports to make this company happen. So they basically, a lot of startup company, they don't always success. So within 15 years, all the 75% of the company that open for the newest technology or anything, they will shut down, because there is a competition, there is a innovation, and if you cannot continuously innovate, prepare to shut down. I don't know whether you guys still remember or not. Nokia phone used to be a very popular when I was getting the first phone, but these days we cannot even find this Nokia phone anymore. So if you cannot continuously innovate, is prepared to shut down. So what can we do in terms of this, something like the Nepal? So Nepal, we are just learning, and small country, no resources. But for the developing country like Nepal, they're replicating the massive multi-billion dollars infrastructure like the US laboratory system overnight is not realistic. So it's not only realistic, I think I would say it's impossible in our lifetime. So, but at least we can start doing something. They centralize and create a shared national user facility, at least one in maybe 5 different places in Nepal. Focus exclusively on the regional strength. So what we needed in the whether in environmental science or agriculture science or the technological hub, and also the implement the tech transfers pipeline early, means whatever you develop something, we need to make it happen. Or if there is no product, then nothing we can do, but just on the paper or in the lab. The other thing is, we can leverage the diaspora with these international people. We know we are not only in US. There is a lot of Nepalese or people all over the world and working in the many national labs, and also the big large industries. So this is one of the things we can actually do in terms of the how can we improve our research and be competitive between these two giants, where India and China is taking over everything. Okay. So for that reason, actually, we started the initiative a long time ago. Whatever we can do as those people who are outside in the Nepal. So we started almost 8 years ago. We formed an organization which is non-profit registered in USA, Association Nepali Physicists in America. Currently, I'm serving as a president. So what we try to actually do is we actually try to engage the collaboration within the people outside the US and also from the Nepal. I'll highly encourage you. Some of you who are not aware with our program, go and look into npaglobal.org. We have done a lot of works within US that's useful for the US communities and also from Nepal. So we have actually started a mentorship program. Several of the students actually did their thesis with us, their bachelor's thesis and master thesis, having the mentor outside the Nepal. We also host monthly talk series, something like this one, the different topics. We do some publication, newsletter, and conference proceedings. Our actually NPA conference, this is our 9th NPA conference, actually hosting in a hybrid model. It will be over the WebEx, in person here in USA, and also we'll be having the conference in Central Department of Physics. If you are interested, you can still register because abstract submission deadline is already done. It will be July 24 to 26. In July 24, it will be Central Department of Physics, so it will be in-person conference there. That's what we call the annual scientific conference. We also do a lot of teaching workshop. A lot of faculty around here is also involved in the how to improve the physics teaching, not only in the college level or the PhD levels, also in the high school level. We have a lot of Nepali physicists working at high school physics teacher are here. We do a lot of sessions about the quantum computing and machine learning sessions. If you are interested, you can join into the npaglobal.org and also the summer and winter coding classes. As someone who is staying in Nepal, they can register as a associate member, so they can get the benefit that the actual member can get it. So, okay, so this is my background about this the national lab system, and then working in the national lab and what we can actually do. Basically, be in touch, work in collaboration, and then our community here is always happy to help. So if you have any question, I can take a briefly pause, and then I can go ahead and then talk about a little bit about my research area. Okay.
Excuse
Then
me,
I'll
sir.
keep. Yes.
So you told us about the ANPA conference, right?
Yes.
So what do you usually discuss about in the conference?
So it's basically scientific research talk. Everyone does. I mean, it's like a conference. You know, you present your research to the community.
It's like we go there and present our research and discuss with each other, things like that.
Yes. Yes.
Okay, thank you.
Yeah. So this one is we already have stopped taking any abstract so far because we already reached our limit. but you can still, if you're interested, you can go there 1-day workshop and then learn what the other people are doing. The most of the talk in person in Kathmandu will be the research done in Kathmandu, but there will be a couple of couple of online talk from outside outside Nepal, presenting remotely, and then on that day, which is July 25th, will be in the in-person talk. There will be a poster session because we cannot accommodate everyone giving their oral presentation. So there will be a poster session, and it will be a good product if you can make some collaboration, talk to other faculty at, basically Central Department of Physics, the professor there, student, or the PhD and master's students.
Thank you, sir.
Okay, so a little bit about my research area. So I'm not going into details of this one. So what is accelerator physics here? Accelerator is nothing new. So there are, right now, if you're talking about, there is more than 30,000 accelerators around the world, small or the big one. But we're talking about the big accelerator project right now because these takes a lot of money to build those small accelerator. When you go to the CT scan or NMR machine, those are also kind of the accelerating systems. But these large accelerators mostly are US, and then also in the European side, some are in China and Japan. And even in India, I think I only know like 1 or 2 accelerators, big large scale accelerator so far. You can see that there are several kind of accelerators around the world. These are the research accelerators, not the applied accelerators. The accelerator are basically you accelerate in charged particles. You cannot accelerate any other thing. So electrons accelerators or the protons accelerators. And then also accelerators are 2 kinds. One is colliders, means you can have a head-on collision between the charged particles, or you can have a stationary target and then collide with all fast-moving charged particles. So for example, Jefferson Lab is a stationary target. And if you have heard about the CERN, which is the head-on collider. And there are several accelerating projects being under construction. Basically, China is taking a lead on making this big, large accelerator for the future science project. And on top of that, not all accelerators are based on the superconductor. So the superconductor are also a special kind of accelerator. Superconductor, whether you know or not, is basically a metals, but when you cool down at low temperature, this becomes superconductor. I'll go through a little bit of more details later on. But right now, there is a lot of accelerators also based on the superconductor science and technology. In US, I'll give you just a screenshot. That's I showed you earlier. The Jefferson Lab is the one of the accelerators. And in terms of the big accelerators, USA has a couple more of those. One in the California, one in Michigan, and there is another big accelerating particle accelerator is we call a XFER for free electron laser. It's in Germany. Basically, as you can see, all of these accelerators there, electron starts from this end and accelerate the charged particles. This XFELs means when the high velocity electrons is passed through the magnetic field, is produced the so-called X-ray or the free electron laser. I'm not going on the details and how actually this can happen. So the accelerator can be used for very different process, different application. For example, here the SLAC, which is the Stanford light source, it also uses the same technology as the XFEL. The electrons accelerate from one end to the other end. Is a couple kilometers long, and it's produced. The light source can be used to understand the fundamental physics. The FRIB does not use an electrons, but is ions. So it's heavy ions accelerated through the charged particles, and is basically use all of these nuclear physics, also the light source. So one of the important thing to understand between these things is if the accelerators are the linear accelerators. They use these superconducting or normal conducting RF cavities. What are the cavities? I'll tell you a little bit later on. And also there are some particle accelerator goes around the circle. Probably you have already known about the CERN, which is the Large Hadron Collider in Geneva. Also the KEK, which is also located in Japan. In USA, there is also called the Advanced Photon Source, which is also synchrotron light source. Basically, this one goes with the electron. And this facility is recently closed. It is also called the relativistic heavy ion collider. But we are building another collider right now. So all of these in the circles means these use the high power magnets. Means when the charged particles are accelerated, they need to bend around in the circle. So we use superconducting magnets. So this relativistic heavy ion collider, which is being shut down right now, is being replaced by this next generation of electron ion collider. So electron ion collider means the electron and ions moves in the different directions, and they make this big collision and try to explore the particles beyond the quartz, gluon, and plasma. So one of the projects I'm currently working on is to making the superconducting cavities for this big electron ion collider. So what is SRF? SRF is we call also superconducting radio frequency cavities. This was actually also the first use was done a long time ago. The Jefferson Lab was the first national lab or the largest facility. They used this superconducting technology in 1985. And then so far, we have more than 338 cavities were installed. But this is the one of the thing is this is the one of the first use of superconducting cavities in the linear accelerator. Before this one, people used to use just normal conducting cavities. These are just the same example as last time. What we do here at the Jefferson Lab, basically my everyday works is design, make the SRF components, cavity, waveguides, and then also because these are the superconductor, we need to cool down at very low temperatures. And also the assist the accelerator operation during this big machine does not always work the way we want. There is something is wrong all the time. And also try to fix those things so that the nuclear physics research can happen without any interruption. Not only the cavity design, we also try to do some other technology, try to improve the performance of this machine, and also try to use this technology to the industrial application, not only the fundamental science, and also try to find the other application, for example, the quantum information science, superconducting qubits, resonators, and other kind of detectors works. So what are the SRF cavity? How does actually this works? So SRF cavity is nothing really interesting thing, because these are just the LCR circuit. So what do you mean by the LCR circuit is any resonance structure has its own self-capacitance, self-inductance, and self-resistance. So basically, when you store some energy in this LC circuit, you can store it in either in electric or magnetic fields. So this structure here, I gave you some small example of this structure where we need to provide the large amount of energy to the charged particles so that this can accelerate and gain more energy. But when you have this electric field, there is also the magnetic field, so that the cavity design is made in such a way that you always try to have a maximum electric field and minimum magnetic field. And then the parameter that we try to always understand is when there is LCR circuit, probably familiar with this one, so called this the quality factors. So quality factor is basically how long or how much energy you can store within that electrical circuit or within that cavity. So these are cavities, as I said earlier, is made from superconducting cavities. Then these are used in the AC field, not the DC field. So these cavities, I show you here at the bottom. This is the the hollow structure. Inside here, we create the high electric field. When the electron, the charged particle comes here, these are AC waves, means when this electrons see the positive field, and when you move on to this side, it fills the positive field back again, because these are oscillating back and forth. So when the electron comes from here and goes from here, this the energy is of the electron is basically a charged particle times the electric field. And then this structure can provide this mega electron volt or the megavolt compared to the DC capacitor or the DC electric field. So if you remember, like if you need to get 1 volt meter, then you use the 2 capacitor plate, apply the voltage 1 volt within a distance of 1 meter. Imagine this is 1 meter long, this cavity, and this 1 meter, within that 1 meter, you can create 10 to the power 6 volt per meter of the electric field using these superconducting cavities. That's the strength of the superconducting cavities that the particle accelerator use. So for example, if we make the very high intense electron beam, imagine using the DC accelerators, how long it need to be. But if you use the same, wanted to get the same amount of energy, then you can actually reduce by a factor of 6, which 10 to the power 1 volt versus a megavolt. Shorter accelerator, where you can make this same energy accelerator. So one of my main research right now is how to improve the performance of the superconducting cavities. This just give you an example about this why superconductor is important. You can if you make everything with the copper or normal conducting, the quality factors which give you the figure of merit of these structures is about 10 to the power 6 difference between the copper versus the normal conducting superconducting niobium cavities. So these there is a lot other advantages of using the superconductor. I'm not gonna go in details as of right now. So what is superconductor? Superconductor is basically conduct electricity without any resistance, but that's only the DC case. But if you have the AC, there is also the finite amount of energy or the current loss in the superconductors. So superconductor research started a long time ago, more than 110 years ago, 115 years ago. But over the first 60 or 70 years ago, people not able to get the high temperature superconductor. But in around 1985, 86, suddenly the superconducting temperature starts to go up. And recently, there is some rumor about the room temperature superconductivity, but these are still need to be verified. The research of this application particle accelerator we do right now still discovered in 1930. So the niobium, which is the elemental superconductor discovered in around 1930s, that is still the material of choice for this current superconducting technology because of this special about this niobium. But however, we try to improve the performance, looking for a better superconductor all the time, but so far there is no luck. So we still have to stick with superconducting niobium cavity. Why niobium? This niobium is readily available everywhere. This is also the highest superconducting transition temperature in terms of the metals, and also these higher critical fields. That's why, although we are trying to explore other superconducting materials other than niobium, but these are very complicated to make this kind of shape. So it takes some more research to make it actually happen. So how do we actually make these cavities in house? So this is what we do at Jefferson Labs. At Jefferson Lab is not only the research facility, we also make these superconducting cavities, and we provide these superconducting cavities to other national labs. So other national lab, wherever you see this superconductor-based technology, at least in the US, we make those in-house here and also send it to the other research facility. Just to give you an example, this is a lot of machining and then hands-on work we need to be done. So basically, we start with the niobium sheet. This is a pure metal, just looks like the plate of aluminum, but it's made from niobium, very pure niobium. We just make a disc. These are the manufacturing processing. We made this in the cup shape. We do these electron beam welding to everything welded together, and a lot of processing happens in between before it goes to the superconducting cryo modules. And then all these cryo modules we call cryo modules, means these structures are inside the cryogenic temperatures. So it means these are cool all the time at 2 Kelvin using the liquid helium. So and then finally install in the tunnel. And why in the tunnel means these there is a lot of reason. One of the main reason is this can produce a lot of radiations, and then people don't want to expose to the radiation, so they are mostly underground. Also, we need to pay attention about the vibration and other things that can actually change the performance of this cavity, and also the electron beams or the charged particles beam. So most of the accelerators are made underground. These are basically our Jefferson lab. We make this kind of structure in-house. Most of these are these, the one of the kind means everything we design, we make the first prototype in-house, do the verification test, and if this works, they can be used in the machine. If not, we try to find something else. So you can see it's going around. It looks different, funny shape. I don't want to go through all this shape, why these are useful, but the depending on your application, whether you are accelerating electron or accelerating protons, and then also the what kind of application you're trying to do, nuclear physics research, or also use some applied research, then this shape and size can be vary. So we not only provide this kind of structure for the US, we also provide for example, the CERN. We provide this cavity to the CERN so they can use their accelerator as well. So the art of this high performance superconducting cavities is very complicated because these are made from superconductor. Basically, my research currently is going around how can we improve this performance of these superconducting cavities. There is a processes. So process means we have to have a new design, new kind of superconductors, and how do they actually process it. And when you do this change in processes, your properties change, means superconducting properties with electronic mean free path, superconducting gap, critical fields, penetration depth, and other things. And finally, we use this one to make in the cavity. So basically, the cavity, we measure all the cavity properties. And the problem here is if you change one, the other one, if it goes one goes up, other goes down. So we are having continuously improving the performance of how to make this performance. We call the high Q, means high quality factor, where a lot of energy can be stored in one of the cavity. And also it can provide the high accelerating gradient, so that we don't need to make several kilometer long particle accelerator, so that we can have to reduce the size. So smaller the size, it's easy to maintain, and it's more cost effective way. Okay, just to summarize here, United States government heavily invests in the fundamental research in the initial stage of invention, and then technology is provided to the private business for the innovation. So basically, invention and innovation, which is very important things to do. So if you have some ideas, the idea sometimes stays in the lab or writing in the paper, But if you cannot translate that into the innovation and then the useful things, it just dies right there. This model is one of the reasons that the United States become the global leader in technology development. The government often absorb the early scientific risk, means they invest a lot of student scientists and also the infrastructure so that they can actually invent something. And when there is invention happens, then the industry drives the commercialization and market adoption. So the Jefferson Lab is one of the 17 national lab, which was the particle accelerator, basically invested in the fundamental research. Sometimes the new technology come out from this one, but most of the work we do is for the fundamental study. So right now, about more than 30 Nepali physicists are directly involved in the research at Jefferson Lab, including myself. So with that, so if you have any questions, I'll take you some questions. Thanks a lot.
947.
Thank you so much, sir, for that deeply insightful and enlightening presentation. Okay, we have some questions in the chat, I guess.
Okay, so I can read here that if you don't mind. What do international laboratory usually expect from the students applying for the internship or research programs? In Nepal, usually we do not have much experimental research experience. Yeah, that's the that's the critical things. You know, when I even come to US, I wanted to be a theoretical physicist because that's all I know, right? I didn't even know the experimental research. But when I come back here, I need to switch to the experimental research because not like I wasn't good at the theory, but it's always challenging to find the theory. So, but the international laboratory usually, not all laboratories offer the internship and program, but there is always a visiting program that actually can come to the United States from outside the outside countries and do their research. Our lab also has some of those programs, but again, the current political scenario is not that great, but we can actually explore those options. So the second one is, what are the current major research gaps in accelerator science? Can we start our career in the field from Nepal? I'm currently undergraduate student in Nepal. As I said earlier, the accelerator, in terms of if you're gonna actually do some applied research, it's harder because it's need a lot of investment. But fundamental understanding about how the accelerator works, how can we make better? Yeah, of course, there is something we can do about it. I think even the small scale accelerator, that's the making a small scale accelerator should be possible, but not for the high energy accelerators. Are there any fellowship opportunity for Nepali students at Jefferson Lab? As of right now, I would say there is no direct fellowship from Nepali student, but sometime we can host as a internship kind of things, but that still need to be in. Have to have a mutual collaboration between the host institute, not individually. No, I think if you are working on the like TU and wanted to come here for 3 months or 4 months, that is still a possibility. So is it possible for Nepal to build its own accelerator facility in the future, even at a small research scale? Yes, I would say yes, because we don't have to go to superconducting because many things can be done with normal conducting. Normal conducting accelerator is also an accelerator, and we can still do a lot of research out of it. Superconducting is only needed if you have a need to go to much large energy scale, but a lot of accelerator can still be done with the low energy skill, because it's not fully understood everything. Okay, any more questions?
If you guys have questions, you can just type it out or unmute and ask yourself.
Yeah, if there is a question, then I'd like to ask the organizer. I don't know who is here. Who is the main organizer for this one? Diksha?
Yes, sir.
Okay, what kind of initiative do you guys do here in this using this what is called NSSR?
So NSSR, basically a Nepali Society of Student Researcher, is a community driven by students, undergrad students mainly. नेपालमा there are no exact त्यति धेरै रिसर्चरसँग कनेक्ट हुने अपर्च्युनिटिज एन्ड डिरेक्ट मेन्टर रिसर्चर अर स्टुडेन्ट्सहरूलाई कनेक्ट गराउने प्लेटफर्म्सहरू चाहिँ त्यति धेरै छैन नेपालमा एन्ड इभन इफ दे आर देयर they require like a lot of criteria and stuff like that. So NSSR is like a bridging situation here. We just connect mentors and researchers who are interested in research and who genuinely wants to be involved in research. We connect mentors all over the globe and students. So we are an organization of students, mainly students. So we just connect students and researchers around the world. We also do workshops and online talks like this. Yeah, and we give some sort of training for scientific writing, how to get into research, and basically we also have like research groups inside us that are involved in research, such as mainly in physics. Such as plasma physics and foundation of quantum mechanics, material science, and etc. So yeah, NSSR just bridges the gap between the students and the mentors in a brief.
Yeah, that's great. I see like a lot of at least right now 38 people joining undergraduate and interested in the physics and physical research. That's great. So as I said earlier, we have a dedicated organization here. If we can help anything, ANPA, you can reach out to us. We can connect with the like-minded researcher. We also do like a problem solving or session sometime. If one have a problem, then yeah, we can collectively sit together and try to find the solutions. Some of our friends are the community member also started entrepreneurship, making means this having small companies and then also do some research. And on those cases, it also be there's some opportunity to contribute to those programs as well. And in terms of the computing and then programming and then lecture, monthly talk, as I said earlier, you can sign up as associate member, where you get all the benefits and also get an up-to-date information on this thing.
Okay, thank you, sir. So we also have one more question in the chat.
What career opportunities are available in foreign countries after completing undergraduate physics in Nepal and challenges? Oh, this is the very hard thing, you know, if you have like undergraduate in physics from Nepal, there is very limited, you know, I mean, to be honest, I need to be honest here. People all over the world trying to come to US and then also in the other countries. So it's not like give a preference of one country over another. But if you have some skill, for example, most of the undergraduate in engineering comes with a skill. That's one of the problem having an undergraduate in basic science is, you know, all the knowledge you needed, but not saying in particular to someone, but we don't have a skill like the research skill or any other technical skill. So which is going to be really challenging. So having this mentality of research, presentation, or even the writing a paper, those things will be actually helpful. But just for the careers, I think the best career is to finish undergraduate and find your PhD somewhere. So that's gonna give you the best. But these days, even after 4 years of bachelor's degree, you can get a admission to the master and PhD program, which wasn't the case for me myself. So I had to come back here and do another master's myself. So yeah, I'm sorry, I don't think I can actually give a correct answer to this one.
Excuse me, sir.
Yes.
So how did you get into Jefferson Lab? Did you apply to it normally, or did you get recommendations from someone else? How did you get into Jefferson Labs?
Yeah, I actually applied it and they invited for an interview. I gave interview and I got selected. That's kind of sometimes. Yeah, I mean, the you have to be how can I say, sometime you have to be the right person at the right time. So not always कति केसमा चाहिँ नेपालमा भन्नुपर्दा कति केसमा even you are doing great, that job may not be you, they may not for you, but sometimes if they are looking for something and if you have the right fit, and you will get there. So that's the thing.
And were you always interested in particle accelerator and superconductor accelerators, or were you interested in that?
Okay. So basically my PhD was in superconductor, but not in particle accelerator. So I came to JL Lab to understand the superconductivity in the beginning, because that was my PhD research, and then that's what I had my expertise. And later on, I changed it to the slightly different. These days I do most engineering kind of things. We make things, test, and then validate the product, and also the a lot of undergraduate and graduate students. So I mentor a lot of graduate and undergraduate students for these days. So it's not like I wanted to do accelerated physics, but just accelerated physics happened to come to me, basically.
And another question. In J Labs, are there more number of engineers or physics passed out graduate, postgraduates?
Yeah, JLab is, as I said earlier, there is more than 2,000 students in postdoc. They come to do their research, right? But very few of them actually can stay at the JLab. So it's really competitive. Right now, I had my student, अर्को नेपाली student हो, मसँगै PhD गरे. He's after finish his PhD, now he's a staff at Jefferson. There are in even my department means I work in the accelerated department, so we have 4 from Nepal. 2 of them were actually did their research and then they graduate and they stay as a staff, and one of them is I actually hired as a postdoc for like 4 or 5 years ago. He worked with me for 2 years and then now he's a staff there. So yeah, sometimes you have to be a right person at the right time. So but there will be a lot of opportunity because doing PhD research and learning is not like a you can actually work throughout your life on the same field. This is actually basically learning how to manage the project, how to do the research, basically gain the skill you need to success in your life. So whatever I did in my PhD is probably I even forgot what I did in my PhD. So that's been that long ago. So.
I see. Thank you, sir.
Okay, do we have any more questions? Okay, I don't see any questions. So, okay, as we come to the end of this session today, I would like to express our sincere gratitude to Dr. Pasupati DHAKAL for sharing his valuable time, expertise, and experience with us. Your journey from Nepal to contributing as one of the world's leading research laboratories serves a powerful reminder that curiosity, dedication, and perseverance can open doors to global scientific opportunities. I would like to extend my heartfelt thanks to our participants for your active engagement and thoughtful questions and enthusiasm throughout the event. Before we officially conclude, we'd love to capture this memorable occasion with our speaker and attendees. I kindly request everyone who is comfortable doing so to please turn on your cameras for a photograph. We will wait a few moments for everyone to join in.
Yeah, and also like to see your face, guys. Don't be scared. I think I know one person there, Devendra Rajupadhyay.
हेलो सर नमस्ते गुड इभिनिङ
नमस्ते, के छ खबर? ठिक छ नि त?
ठिक छ सर ठिक छ भेरी नाइस प्रेजेन्टेसन थ्याङ्क यू सर
Yeah, Devendra is also the right person there to ask about these research opportunities and then other like the presentation opportunity that can be available around the US. I think Devendra, you've been here a couple of times, right?
sir I got an opportunity to visit Jefferson Lab last year 2024
Yeah.
Okay, I guess the photo is clicked. Thank you guys for joining. That was wonderful. Okay, to stay updated on our upcoming guest lectures, mentorship programs, research workshops, and other opportunities, please follow NSSR through our official platforms and stay connected with our growing research community. Once again, thank you, Dr. DHAKAL, and thank you for our participants for joining us today. We hope to see you again at future NSSR events. Have a wonderful night, I guess. Okay, stay curious, keep exploring, and keep researching. This concludes today's session. Thank you and good night, everyone.
Okay, thank you, everyone. Look forward to get connected again next time. So.